Alright, so now what we're going to do is we're going to look at two more tests. So, to add to our ever-growing list, right? So, this was the notes from the previous section, but I'll just add to it anyway. So, in this section, we're going to look at what we call the direct comparison test and the limit comparison test. So I'll add them to our list. So two more tests to use to determine if an infinite series converges or diverges. So we're going to start talking about direct comparison first. So the comparison tests, there's direct comparison and there's limit comparison. We're going to do both, obviously, but we're going to start with direct comparison first. But before we actually get into the details of direct comparison, so before we actually get into the details of this test, we need to look at another type of series. So we didn't mention this series yet, but it's very important because it shows up a lot when using direct comparison and limit comparison. It's a specific type of series that I was going to mention earlier, but I decided to hold off until this section. It's not a big deal, but it is something that I do want to talk about. And this particular series that I'm talking about is called a P-series. So before I actually start talking about direct comparison tests, I want to talk about a specific type of series. So note, before we look at this test, we need to examine a specific series called a P-series. So yeah, a P-series. So a P-series looks like the following. It's a series that takes the form, the sum from k equals 1 to infinity of 1 over k to the p power, where p is positive. So this is what a P-series looks like. So we know whether it's just a ratio series, and we know this about a P-series. It converges if the value of p, so the power of this variable down here, so it converges if p is greater than 1, or it diverges if p is less than or equal to 1 or greater than 0. So this is the important stuff you need to know about a P-series. So for example, the series 1 over k cubed. Well, does that converge or diverge? Well, that converges. Since, what's the value p here? Well, the value p is the power of the k value in the denominator. There it is, right there. Since p equals 3, which is greater than 1. And we say up here, if it's greater than 1, it means it converges. Otherwise, if it's between 0 and 1, including 1, it diverges. So that means it converges. So, you know, whenever we look at a p-series, as long as you state the value of p is greater than 1 or between 0 and 1, that's enough to conclude that a p-series converges or diverges, because by definition, that's what a p-series is. Here's another example. One over the square root of k. Well, if you rewrite this as 1 over, if you just rewrite that, that's instead of square root of k, you could just write k to the 1/2 power, right? Well, does that converge or diverge? Well, this diverges. Since the value of p here, since I rewrote it this way, I can see that the value of p here is 1/2. And 1/2 is less than 1, or equal to it, so it diverges. And, you know, that's just a basic idea. Just the basic form of what a p-series looks like, and that's really it. I do want to make a note here, however. There's one additional piece of information I want to note about this, is that this particular series, 1 over k, well, if you look, this, you know, the value p here is 1, right? So this is actually a p-series. You know, if I were to look at the power there, this is actually a p-series with p equal to 1. Now, instead of calling this a p-series where p equals 1, this actually has a specific name. This is called a harmonic series. And harmonic series always diverge. Harmonic series diverge. So if you ever have the series of 1 over k or 1 over n, you know, same thing, it's a harmonic series, and that's important to note. A harmonic series is known to diverge. Otherwise, if you have a different p value here, then it's just a p-series. So these are important series you need to know about, because they show up a lot when we look at comparison tests. Okay, so now that we know what a p-series and a harmonic series look like, let's actually look at the direct comparison test. Alright, so the direct comparison test is the following. And basically what it does is it compares, so note, it compares, obviously, because comparisons in the test, so it compares the given series to a known series to see if the given series converges or diverges. And I want to emphasize a word here. So we compare the given series. So this is the series to start with. And when I say a known series, that means that's an important concept right there. That means if I'm comparing it to a known series, typically, when I use direct comparison, typically that is a P series. That's why I show them to you, because they're important to know. They show up a lot with this kind of test. So usually a known series, I'll just say here, typically the known series is a P series or harmonic. That's not always the case, but I would say like 90% of the time, even 95% of the time, this is typically true. And the way we use the direct comparison test is we take the given series and we compare it to a known series, which is typically harmonic or P series, and we see how they relate. If one is greater than the other or one is less than the other. So then by comparison we could say, all right, well then since this one converges and diverges, then we can say the same about the series we started with. So what I'm really doing here is so here's the actual test. Let me actually, I could probably squeeze it in here. So here's the actual test. So let A of k, which starts at some value to infinity, and B of k, so I have two individual series with positive terms. There's that word again, positive terms. All right, so I have two series of positive terms. So I have one of two possibilities. The first possibility is if A of k is greater than B of k, so that means the A series is greater than the B series for all k, and I know something about the A series. In other words, I know that A of k converges. Then I could say, by comparison, B of k also converges. Let me just write down the second one and I'll kind of graphically represent what I mean. And in the other case is if A of k is greater than B of k for all k, and I know something about B of k in this case, and B of k diverges, then A of k also diverges. So this right here is the essence of the direct comparison test. And let me just stick in a graph here. It's a very simple graph. I'm using a credit card for my ruler. Because, well, I left mine at school and I can't get into school now. So so this graph is going to represent case 1 and case 2 separately. So let's say I'm looking at the first case here. So I have two series, A of k and B of k. And I know my assumption, let's say I know this. If I'm saying A of k is greater than B of k. So if I drew two series on here, on this coordinate system, let's say this graph represents the series A of k. All right, and let's say this one represents B of k. I know this is true because A of k is greater than B of k, so that means A of k is going to be above this one because it's greater than it. And if I know that A of k converges, so let's say this horizontal axis right here is my value m, right? So if A of k converges to m, right? Let's say that this series converges to this value m, then what do I know here? I know that A of k converges to m, right? So anything less than it, which you could see by the graph, is going to have to do what? It's going to have to converge to m as well, because it's caught between something that converges and the value that it converges to. And that right there is the essence of the direct comparison test. I know this, which is dictated by the graph, and I know that A of k converges. So anything below A of k that converges must also converge as well. That's exactly what that says. And if I draw the graph of condition 2 over here, so, you know, this inequality is still the same. Here's A of k. Here's B of k. And here's the ratio, and here's the value m. Right? Well, what do I know in case 2? I know this is true, and I know that this is true. So if this is greater than this, which we know, and in this case, if B of k diverges, so that means B of k is not going to converge to m. It's going to actually go off in this direction. It's going to go off in this direction. So if this diverges, it's not going to do this. It's actually going to take off like this. It's actually going to take off. My bad. Just bear with me for 1 second. All right. So here's A of k. And here's B of k. I know that B of k diverges, so instead of going down to m, it's going to go off like this. That's what I meant to do. Sorry about that. So because B of k diverges and A of k is greater than B of k, it must be above it, right? So if B of k is going to diverge, anything above it is going to diverge as well, and that's what this says right here. So these are the two cases of the direct comparison test. Basically, if anything that's caught below something that converges, it's going to get caught below it. Anything that's above something that diverges is going to get caught above it. That's essentially what it says. So let's kind of, look at a few examples here to see how we use the direct comparison test. K cubed plus k plus 7. Determine whether that converges or diverges. All right. Now, if you did what's the first test we learned? The zero limit test. If you did that here, you should see pretty easily that that goes to 0, which means it doesn't work. All right. What's the other test we learned? The integral test. Do you really want to integrate 1 over k cubed plus k plus 7? Probably not, because that would require partial fractions, and I don't know how to factor this. So if I don't know how to factor it, you're probably not going to factor it. So why don't we use direct comparison? So here's what we do. Yeah, does this series have positive terms? Yeah, that's pretty easy to see. So instead of using the integral test, I want you to look at the dominant terms here in the series. So the numerator is just 1, okay. But what's the dominant term in the denominator? It's k cubed, right? That's the dominant term down there. So let me make a little note here. So note, when k is large, the k cubed term should dominate. Right? So now that I know that, let me pose this question. How does 1 over k cubed plus k plus 7, how does that compare to 1 over k cubed? Because what I'm saying is I'm taking this, and since this is the dominant term, I don't care about 7 or k, right? If I just cover them up, when k gets large, right? When k gets large, the k cubed term dominates. So that makes k and 7 irrelevant. So I end up getting 1 over k cubed. And that's what I'm asking here, right? How does this compare to this? So I want to compare this to this. All right, well, the idea here is to take this and compare it to this. How do I do that? Well, here's what we're going to look at. Right? So here's what I started with, and how do I get to this? So at some point, so I started here, and I'm going to do some algebra, or I'm going to do some math that gets me to here. There's going to be some stuff in between, but just bear with me for a second. So, so I want to do some algebra to this, or some math to this, that will get to 1 over k cubed. So what if I make the bottom of this fraction? So what if I take away 7, right? So you're thinking, all right, how do I get this to be this, right? Well, you could subtract 7 and you could subtract k, right? But how will that affect this fraction? Will that make it bigger, or will that make it smaller? Well, as it turns out, I'm going to make this in a note here. So note, if you make the bottom smaller, right? If you take something away, if you make the bottom smaller, the fraction, so if we make the bottom smaller, so if I subtracted the 7, the fraction actually becomes bigger. It gets bigger. And this right here is the important thing. So if I take 7 away, right, then the next fraction, based upon this note, is going to get bigger. So in other words, I have a less than symbol, because this term next to it's going to be bigger. So if I subtract 7 from there, I'm going to have 1 over k cubed plus k, right? This fraction is bigger than this fraction because of this note. If you make the bottom smaller, aka subtract 7, right, the fraction gets bigger. fraction gets bigger. And that's denoted by this right here. Hopefully that makes sense to you. But, you know, so how do I get from this fraction to this fraction? Well, could I subtract k? Sure. Now subtract k. So if I subtract k, then the same note here still applies. I took something away from the bottom. The bottom got smaller, so the next fraction is going to get bigger. And when you subtract k from here, you're going to get 1 over k cubed, which is equal to that. All right. Well, that's good. So this is mathematically true now. All right. So now that I made this, I've made a true mathematical statement here, right? This is less than 1 over k cubed by doing some mathematical comparison, right? What do I know? So here's the idea. What do I know about this? What kind of series is that? It's a p-series. Remember how I said that down here? Typically, when I compare a given series to a known series, that known series is a p-series. Ha! There it is right here. Here's the starting series, and I'm comparing it to a known series. This is a known series. This is a p-series, right? Where p equals 3, which is greater than 1, which means it does what? It converges. So, all right. Well, that's interesting. So, if this series, so let me make my graph here just to illustrate my point. So, I don't know what it converges to. I just know that it converges to some value m, right? I know that this series, so I could treat this series as like my b of k series, and I could treat this series, my starting series, as my a of k series. All right. So b of k is greater than a of k. All right, so that means, and b of k converges. So I know that b of k is converging to m, and and this is b of k right here. But how does a of k compare to it? Well, a of k is less than b of k. So that means it's below it. So because it's below this, and this converges to m, what does a of k do? It must converge to m as well, because it's sandwiched between b of k and m. It's sandwiched between. So because I have that, because I have this, the direct comparison here will work. So because my comparison holds, in other words, my comparison is set up correctly. So let me just make a note down here. Note, since my comparison, or my direct comparison, is set up correctly, the direct comparison test works. Now, don't worry if you don't know what I mean by this right now, because as you'll see in additional examples later on, sometimes I could do this, but it won't be set up the right way, and direct comparison won't work. But in this case, it does work, because b of k is up here, a of k is caught between this converging and m. Like, for example, if this right here were diverging, then a of k could still do whatever it wants. And if that were the case, then the direct comparison would not work. So don't worry about that. You'll see what I mean. But so since this is set up correctly, this is caught between something that converges to m and the value itself, m. I could say, therefore, Since this converges and it's less than that converging, therefore this series, the original series, 1 over k cubed plus k plus 7 converges by direct comparison. I hope this makes sense. Now, it could be a little obtuse to wrap your mind around initially, but with a little practice, it kind of starts to make sense. You know, the magic of this method is right here. This is what you got to do. But sometimes this won't work. Before we see an example that doesn't work by direct comparison, let's look at a few more examples. Okay, here's another example. K equals 17, oh man. Yeah, where it starts is really irrelevant. It starts at k equals 1, k equals 0, k equals 10, whatever. Of sine squared of k over k times k plus 1 converges or diverges. So determine whether that converges or diverges. All right, well, you could do the zero limit test, but that won't work. You could try it. You'll see it won't work. You're not going to want to integrate that. That's ugly. So let's try direct comparison. Does this have positive terms? Yes. By quick inspection, you can see that it's a positive term series. Okay. So since I'm thinking about using direct comparison, here's my original series, right? So start with that. Now, what's the dominant term in the denominator down here? This is factored out, but if you factor it in, right? If you multiply that out, that's k squared plus k, right? So the dominant term here is k squared. So I'm thinking, right, if I ignore the k, I want to compare this to something over k squared. Well, I'm thinking I want to compare it to that, right? And that's a known series. That's a p series, or p equals 2, which means it converges. All right, so I'm trying to get from here to something like that. All right, so how am I going to do that? Well, let me multiply this out. Now, can I do the same thing I did up here? Sure. If I subtract k, what does that do to the fraction? If I subtract k, right? If I take, here's that note again. If you make the bottom smaller, subtract k, subtract something, the fraction becomes bigger. So when I subtract k, you end up getting what? Sine squared k over k squared. Now, I don't really need the sine of squared of k here. I could kind of get rid of that. And the reason being is because, so let me make a note here. Note. I can get rid of sine squared of k because I know So it actually has to do with the range of k, or sine. What do you know about sine? Well, sine is caught between -1 and 1. In other words, sine of k is less than or equal to 1, right? I know this. I know this. This is the range of sine and sine function, right? Sine is caught between 1 and -1. So I could, since I know this, I could just remove this right here. I could just omit that and end up getting this. I could just omit that. So I could just basically drop that and get this. Okay. And that's because of this right here. All right, sine of k is less than or equal to 1, so this just could become 1. All right. Does my comparison work here? It does. This converges because it's a p-series. So I could say now the series from 17 to infinity of 1 over k squared, that's what this is right here, right? That converges since p equals 2, which is greater than 1. It's a p-series. And since this is greater than something that converges, this right here is greater than my original series. And since this converges, it's caught between this series that converges and the value it converges to. We don't know what it converges to. We just know that it converges. So it's set up similarly to this problem right here. This series converges and it's caught below it, so it must converge as well. So therefore, hence, my original series also converges by direct comparison. That's it. You could also say comparison test, and you'll see what I mean because later I'm going to do the limit comparison. But I mean, that's the idea behind it. Provided this work right here, provided the inequality set up correctly, right? You could use direct comparison, but you know, there are some cases where that kind of falls apart. But before that, let's look at another example. Determine whether that series converges or diverges. Okay. So what are we going to do here? Well, so just like I did in the previous ones, let's look at the dominant term. Let's look at the dominant term in this series. So, you know, the power here is 1, right? Well, what's the power here? K. You know, if I ignore the 2, right? I don't care about the 2, but that's the square root of k, which is k to the 1/2, right? All right. So I could think about comparing this to, if I have k to the first times k to the 1/2, right? If I compare this to square root of k, which is k to the 1/2, right? If I think about that and I multiply that by k, right? So k times k to the 1/2, that's going to be k to the 3/2 power, right? Now, if I do that here, well, all right, that's fine. And then I subtract this and I do it the way I've been doing it. I know that this is going to converge and then I'm good to go, right? But if you notice here, I don't have the luxury of getting rid of the square root of k plus 3 like I did with, well, this one just had a 1 in the numerator to begin with. This one was sine squared of k, and I could get rid of it because of this right here, because of the range of sine of k. But I can't just get rid of this one. I can't just do that. So while I might be able to draw a conclusion by making this less than this and then go from there, I can't do it here. So what I gotta do is I gotta try and get rid of, I gotta subtract something else. Not from the bottom, but from the top. So if you look here on this, right, how does the square root of k plus 3 relate to the square root of k plus 2? They're not off by much. This one's just one more than that. So if I take away 1 from here, right, what does this term become in the numerator? It becomes the square root of k plus 2. And then I'll have a square root of k plus 2 down here, which I could do what? I could cancel them out, right? So that looks sweet. Let me try that. So let me make a note here. Note. And it's very similar to this note. If you make the bottom smaller, the fraction gets bigger. Well, in this case, if I make the top smaller, what happens to the fraction? The fraction gets smaller. So that's an important note there. Just like this one's an important note. These are two very important notes when it comes to the comparison test. All right, so if I started with this series, right, and I make the top smaller by subtracting 1 from it, if I make the top smaller, the fraction gets smaller, which means I have this instead, right? This is going to get smaller, right? So when I subtract 1 from here, I'm going to get the square root of k plus 2 all over k times the square root of k plus 2. All right? Because I subtracted 1 from here. If you make the top smaller, which I did, the fraction gets smaller. So now that I have this, and the whole reason of doing this is because, like I said, this is going to cancel out with this. Right? And now what I'm going to get is what? I'm going to get 1 over k. What's 1 over k? What's this? That's a harmonic series. That's a harmonic series. So that's pretty nice. So what can I say here? So this right here, this is an example of case 2, right? What does our harmonic series do? Harmonic series diverge, right? So I have something, if I make my graph here, right? This series is diverging, which means it's going off. All right, let's say this is let's say that's A of k, and let's say this one is B of k. Just, for comparison's sake. A of k is our harmonic series which diverges. So it does this. It diverges. It doesn't go to M, it goes away from M. How does B of k compare to that? It's greater than it. In other words, it's above it. So if it's above it, and this one's diverging, what must it do? It must diverge as well. If it's caught above it, it's going to take off with it as well. So the comparison works here. So since I looked at it graphically, I can, I could justify it to myself and say, all right, it works. Great. So now what I'm going to say is, now the series k equals 1 to infinity of 1 over k diverges, since it's harmonic, and because I know the comparison's set up correctly, because I looked at how this relates to this. This is a known series, and by doing this math trick, I'm able to get to here. It diverges. So anything above it is going to diverge as well. So I could say, therefore, all right, so therefore, my original series diverges by direct comparison. Boom. So whenever you're doing, let me just summarize this. Whenever you're doing direct comparison, you're comparing a given series to a known series. And I usually say the known series is going to be a P series, or, in this case, P series, harmonic series. Now, doing that requires, making use of this tip right here, or this tip right here. If you can get your mind wrapped around that, it's really not hard. It just requires practice and some visual representation to actually get used to it. But we're going to look at another example here. Does this 1 over k squared minus 2, does that converge? Does that series converge or diverge? All right. So like I said, if the inequalities we created, if they go the wrong way, or if they're not set up correctly, like in this case, the inequality went the right way. In this case, the inequality went the right way. In this case, the inequality went the right way. In this case, direct comparison will work. But in some cases, the inequality will not work. This example will illustrate that. So, let me just take a note here. Direct comparison won't work if the inequality goes the wrong way. What do I mean by that? Well, you'll see what I mean. So, again, what's the dominant term here? Well, obviously it's k squared. Alright, so I want to compare this to 1 over k squared somehow. Alright. I want to compare that to 1 over k squared, right? Because that's the dominant term. Well, that's not hard, right? Based upon what we just did, I'm going to make a little note here. Note. If I make the bottom bigger, so if I make the bottom bigger, in other words, if I add 2 here, right, that's the natural thing you would do. If I make the bottom bigger, how does that change the fraction? The fraction gets smaller. So if I add 2 here, the fraction is actually going to get smaller. And if I add 2 here, right, I'm going to get 1 over k squared. Right, which is obviously equal to the one I'm comparing it to. So, yeah. All right. Well, what is this kind of series right here? That's a p-series. Or p equals 2, which is greater than 1, which means it converges. Right? So you're probably thinking you're almost done with this problem, right? Wrong. You're not done with this problem. This actually doesn't work. And you're going to see why. So let me draw my graph here. Let me draw my graph. This is the series I'm comparing it. So this is I'm comparing this to the known. So let me treat this as a of, let me call that a of k, and let me call my original series b of k. All right. Now, what do I know about this series? It's a p-series that converges. Okay, so this series, a of k, converges to some value, m. So that's what a of k is doing, right? How is b of k related to this? Is it above it or below it? It's above it, right? So b of k is above it. Uh-oh, what's wrong? Well, I want you to see something here. In order for direct comparison to work here, this would need to be where? It would need to be below this. This b of k, I was about to draw it, but I want you to see this. B of k here is above it because of the inequality that I made. But a of k, this p-series, converges to m. But if it's above it, that doesn't mean b of k is going to converge because it's not caught underneath it. It's actually above it. B of k could converge or could diverge. So b of k, you know, it could do this, or it could do this. So this is not set up correctly. So let me just make a note here. Note. B of k is still free to diverge or converge. So because of that, direct comparison won't work here. Uh-oh. So, hopefully this is starting to, make a little sense here. I'm drawing the series that I know what it does. It's the known series. This is a p-series which converges, so I know I could draw it this way. How does b of k compare to it? Well, I know by drawing this conclusion with the inequality, it's above it. But if it's above it, it could do this or this. In other words, direct comparison won't work. So what do I do? Well, as it turns out, this is where our next test comes in. And it's called the limit comparison test. So that's what I'm going to look at here. So let me come here and say this. How does this series compare to this? Well, I mean, if you look here, they're not off that much. They're just by a value of 2. So what I could say here is that, the series 1 over k squared is close enough to the series I started with. This series is close enough to this series that I can use limit comparison. So this series is close enough to this series in some sense. ... Which means, don't worry if you don't like. What do I mean by close enough? Well, they only go off by a factor of, well, not a factor, but a difference of 2, right? Actually, I'm sorry, this is supposed to be 2. All right. So this series is not that far off from that series. So what we could do is we can use the limit comparison test. We could use the limit comparison test. And what does this do is the limit comparison test, it makes the idea that one series is close to, and I use that in quotations, is close to another series without having to worry about inequalities. So, like in this case right here, the inequality, yeah, it's true that this is a p-series, but like I've said several times, the inequalities are not set up the right way. I can't draw a conclusion this way because this series could still diverge or converge. So because in this case the inequalities don't work, I'm forced to try the limit comparison test. Okay. So how does the limit comparison test work? Well, so here it is. I'm going to let some series be a positive term series, like you've seen already, pretty common. And I'm going to let another series I'm going to call b of k be a positive term series whose behavior is known. So you typically choose this series because, you know, it's close to the given series. Kind of like this one, right? This series is close enough to this one, right? And this is a known series. It's a P series where, you know, it converges because P is 2. So if you have this, which is set up similar to what I have here, right? This is the series I started with. And this right here is the compared series. Like, you know, 1 over k squared, or usually P series or harmonic or whatever. Then here's the conclusion about. So here's what I could do. If I have this, right, I have my given series and some series that's, you know, like this one. So I'll just say that in parentheses here. Like the A of k series. I want to look at, now it's called the limit comparison test for a reason, right? So I'm going to look at the limit as k approaches infinity of the ratio of A of k over B of k. I can make the following conclusions. This seems like a lot of information, but it's really not. This limit approaches L, right? If L, so if I take the limit of the series I started with and over, you know, the ratio of the starting series and a similar series, and I get L as the limit. So if L is a finite positive number, then the series A of k and B of k behave the same way. So what do I mean by that? If the series I started with compared to the like series, right? If this like series converged, then the series I started with will also converge. If this one diverged, then the series I started with will also diverge. They behave the same way. That's if this limit is a positive finite number. The second possibility. If L is equal to 0, and the series that I'm comparing it to, B of k diverges, then A of k, oh, I'm sorry, not diverges, converges. Sorry. Then A of k will also converge. So if you get 0 and the series that the compared series converges, then the series I started with will also converge. And then the other condition is if L is positive infinity. and B of k diverges, then A of k will also diverges. All right, so it seems like a lot of information in the limit comparison test, but you only have really three cases. L is a finite positive number. So here's the series I started with. If I compare it to something that's like it, like it's close to but not too different, and I take the limit of that ratio, right? I get one of three possibilities. I get a finite positive number, they behave the same way. If I get 0 and the one I compared to converges, then the one I started with also converges. If I get infinity and the one I compared it to diverges, then the one I started with also diverges. All right, so let's see it in action. Let's see it in action. Determine whether one over k squared minus 2 converges or diverges. This is just the one we did, right? But we couldn't, well, this is the one we started, right? We tried to do this one with direct comparison, but it didn't work. Well, let's revisit it now with limit comparison. All right, so we know that the series we start, this is very similar to, and we saw it by the inequalities, it's very similar to that series, right? They're close to each other, right? So we could try using limit comparison. So if I take the limit, as k approaches infinity, so, you know, if we look at the test, right, A of k is the one we started with, right? B of k is the one we're comparing it to. So we started with this one, right? So this is A of k, and this is B of k. So we take the limit of A of k over B of k. So that's going to be 1 over k squared minus 2 all over 1 over k squared. Well, how do we take that limit? So take the reciprocal up here. Times the reciprocal of 1 over k squared is k squared over 1. Which is k squared over k squared minus 2. Alright, well, what's the limit of that? That's easy. K squared over k squared, dominant terms, that's going to be 1. Alright. 1 is what? That's a finite positive number, isn't it? That's a finite positive number. So what do we know about the limit comparison test? Right? And this is case 1. If I have a limit finite positive number, then the series behave the same way. Alright. Well, how does this series behave? We already know. I looked at it here. This is a p-series, which converges. Right? It's a p-series. The limit of their ratio was a finite positive number. So therefore, I could say I know that this converges because it's a p-series where p equals 2, which is greater than 1. And the limit as k approaches infinity of a of k over b of k equals 1, which is a finite positive number. So therefore, what do we know? Since I get a finite positive number of that ratio, I know that the series behave the same way. So since this one converges, then the one I started with, therefore, the series I started with also converges by limit comparison. Boom. So you can kind of see how limit comparison works here. It's pretty nice. If you had, when we looked at it here, we couldn't draw a conclusion this way. So how do we do it? Well, we use limit comparison. We don't have to worry about inequalities that way. Alright, let's look at another one. Okay, so this is the series 4k squared plus k plus 9 over 7k cubed plus 13. Now, if I look at the dominant terms here, right, so the dominant term in the numerator is 4k squared and the dominant term is 7k cubed, right? So if I look at the dominant terms, I ignore those, right? That's going to be similar to, right, 4k squared over 7k cubed. Well, what does that become? That just becomes 4 over 7 times 1 over k. Now, I don't care about the 4 sevenths, right? So if I just look at 1 over k, what does that tell you? Well, 1 over k, that looks like it's harmonic, right? So I could certainly try to construct an inequality relating this one to this, right? 4 over 7k. But I don't know if the inequality is going to work that way. Because, if I subtract 13, right? So if I subtract 13, then this will become greater than this over 7k cubed, but if I subtract the 9 and the k, then the fraction actually, the inequality will get flip-flopped. It'll become less than, and then it'll become greater than. And in that case, I'm going to go in circles. It's not going to really work that well. So direct comparison probably won't work here because you have a lot of terms here in the numerator and denominator. But because I'm looking at the dominant terms, I could say that this series is very similar to this series, 4 over 7k, which is a harmonic series. So instead of developing inequalities, I could try doing a limit comparison. So I could say this series is like four over 7k, or 4/7 times 1 over k. And remember about properties, you could bring this 4/7 out here, like this. This is still harmonic, regardless of what coefficients out here. So this series is very like this series, which is harmonic, which diverges. So, all right, so I want to think about using limit comparison. So let's take the limit of a of k over b of k. All over 4 over 7k. All right, so bring this up as a reciprocal. Times, so the reciprocal of this, it's 7k over 4. All right. All right, well, if I multiply the 7k into here, all right, so I'm going to get the limit, k approaches infinity, of well, let me just distribute the k in. I mean, it'll work out either way. I'm just going to distribute the k in. So when I do that, I'm going to have, so 7/4 is right here, right? So when I distribute the k in here, I'm going to get 4k cubed plus k squared plus 9k all over 7k cubed plus 13, and that's going to be times 7 over 4, because I just factored in the k. The 7/4 is still there. So I mean, you don't have to do it this way. You can multiply the 7/4 in as well and then take the limit of that, but it just makes it look easier. Well, it is actually easier, because if I look here, the dominant term here is 4k cubed. The dominant term down here is 7k cubed, because they're the dominant powers, so I could just ignore the rest. So the limit of that is going to go to 4/7, right? It's going to go to 4/7. So this, right, because this is 4 over 7, or the k cubed, or the dominant terms. So this is going to be 4/7 times 7 over 4. Which is equal to 1. What is that? That's a finite positive number. Right? Finite number positive. Yeah, I wrote it in the opposite order, but you know what I mean. So what does that mean? It means the series behave the same way. So So when I say my conclusion here, all right, the series, so this series right here, I showed it here, but I'm going to summarize it in a good conclusion. Which, you know, if I brought the 4/7 out, that diverges, since it's harmonic. And since I got a finite positive number, and the series I compared it to diverges, I could say, therefore, they behave the same way, which means, therefore, the original series does what? That also diverges. By limit comparison. And that's it. You know, when you're doing these series tests, it's not that it's hard, it's just there's a lot of stuff that you have to remember, but you know, it's actually pretty easy to, I don't know, once you get the conditions of the tests down pat, it's really not that bad in my opinion. So, you know, that's it for this section. When it comes to using limit comparison and direct comparison. So, you know, it takes a little practice, I'm not going to lie. It's not as straightforward as the integral test, but it's very useful to use direct comparison. The integral test is kind of like a last resort. You don't want to try integral test unless you're out of options. But direct comparison is one of the more common tests you're going to see. So what we're going to do now, in the next section, in 10.5, we're actually going to start looking at other tests. And you know, we're not done adding to our list. So we still have a few more tests to look at, but I'm going to add to this list right here. So in the next section, we're actually going to add to this. There's going to be 5, 6, and maybe even 7. I'll have to see, but we're going to add to that in the next section. But when it comes to comparison tests, that's the idea. Direct comparison and limit comparison. You know, we're usually comparing them to a p-series or harmonic series, but that's the idea. So, you know, hopefully, you know, practice will definitely help you get the idea around these tests. But other than that, that's it for this section. So in the next section, we're going to look at 2 more tests, and they're going to be called the ratio test and the root test. So that's the end of this video.